Hey there, and welcome to my lesson that is going to be over parametric equations. Specifically, things that we're going to be looking at. You can see here is the technical mumbo jumbo. Essentially what we're going to be doing in this lesson is trying to identify the derivative of a parametric equation, maybe sketch some parametric functions, find tangent lines to the curve, and we're going to have some calculator exercises that we're going to do as well. But let's go ahead and jump into it here. Here, what it's talking about, in a previous lesson, we talked about how parametric equations were used to represent we use that third kind of variable that we use, that's how we parameterize a function, and that third variable was time that or t, that we generally refer to as time to represent how a particle is going to be moving when we graph a parametric function or a set of parametric equations. Here it's telling you that for the x equation, that's going to tell you your horizontal motion, where your y equals equation will indicate your up and down motion. But what it's telling you here, where do we determine the maximum height? Well, if you remember from stuff that we did in AB Calculus or Calc 1, depending on what you're looking at, we were able to use, say, the first derivatives test to determine when we were going to have relative minimum or maximums. So we can do the same thing here, meaning that we need to be able to know how to find the derivative or the instantaneous rate of change of these parametric equations. And it's going to be a little bit different than what you would have done typically. It's not like a brand new way of doing derivatives. It's just an extension of things that you already know for derivatives. So this first thing that we're going to be looking at here is going to kind of walk you through how we identify the derivative of a set of parametric equations. So we have a set of parametric equations here. X is equal to t squared and y is equal to t cubed minus 3t. And what it's asking you to do, it says find dx dt, find the derivative of x with respect to time, and dy dt. Okay, well, that's not a big deal. So I guess we can probably do these in two different colors. So here, dx dt, we're focusing on this function here. If I wanted to find that, where we have, what is it, x is equal to t squared. So if I find the derivative of that, the derivative of x with respect to time, dx dt, would be equal to 2t. Okay, and let's pick another color here, and we can do dy dt the same way. We're looking at this example here. So we had, in this case, y is equal to t cubed minus 3t. So the derivative of y with respect to time, in this case, would be 3t squared minus 3. So here, like so far, what we're doing is we're just doing the standard power rule for derivatives of a polynomial. What we normally think of as an actual derivative, dy dx, the derivative of y with respect to x, that's what we're going to be looking at now. So if I say dy dx, what I'm really going to be looking at here is I'm going to say dy, and let me clean this up just a little bit here, because this one's going to be an ugly looking kind of fraction to start with. Here we have dy dt being divided by dx dt. So essentially, again, going back to elementary school mathematics, we're dividing a fraction with another fraction, so that's really saying multiply by the reciprocal, which would give us dy dt times dt over dx. And you can see that the dy or the dt in the top and the bottom, those are going to just simplify to be 1, which is where we get dy dt. So this is a method that you need to make sure that you remember. Okay, memorize this method. But in the long run, it's literally going to just be dy over dy over dx. So what we wind up with here, we can take I don't need to change my colors here. We can take this that we had for dy dt, and it will go to the numerator. And what I have here for dx dt, it will go for the denominator. And so what I'm left with here for dy dx, which is what it's asking me to find, dy dx is really just going to be 3t squared minus 3 divided by 2t. So now that we've found the derivative, essentially, of the set of parametric equations that we had, here, this is what we would do to find the second derivative. The second derivative, and again, here, this is going to be something that's not given to you if you have to do this on an AP exam. This is going to be something you need to know what it is and how to do it. So the second derivative, the way that we read that, d squared y over dx squared, because we're taking the derivative with respect to y, or with respect to x, so that's why we square x, the second derivative with respect to x squared, is going to be d dt, meaning the derivative of what we just found, dy dx, over dx dt. So let me just go ahead and write that down there because it's kind of a weird thing. This is what I'm looking at. I'm going to say d squared y over dx squared, the second derivative of y with respect to x, is equal to d dt. Now here, d dt, there's nothing to substitute. It's just indicating that that is going to be the derivative of whatever is in the parentheses with respect to time. So in this case, dy dx is what we got on the last example on part B. So I'm going to put the 3t squared minus 3 divided by, what was it, 2t. We're going to take the derivative of that divided by dx dt. Well, the dx dt was just 2t. Well, let's go ahead and see what we get here. I know that on your papers, those of you that are following along with this stuff on your notes, it's more horizontal than it is vertical, but I'm going to kind of go down instead of sideways. So what we're looking at here, the derivative of the stuff that's in the parentheses, that's the derivative of a quotient. So we have to use the quotient rule, low d high minus high d low over low low. So low will give me 2t. The derivative of the high part will give me a 6t minus high. So here we're going to keep this, all of it in parentheses, and really probably put it in brackets here. We have 3t squared minus 3 times the derivative of the low part, which would just be 2, over low low. So that would be, in parentheses, 2t quantity squared. And all of that is just over the dx dt, the 2t. So everything that's in the overall numerator is the quotient rule of the derivative for 3t squared minus 3 divided by 2t. Low d high minus high d low over low low. So now we can simplify whatever we can in the numerator. So simplifying the numerator, I'm going to wind up with a 12 t squared minus a 6t squared plus a 6 over 4t squared. And instead of dividing by 2t, I'm going to multiply by its reciprocal, multiplied by 1 over 2t. So simplifying a little bit more, the 12t squared and the 6t squared, those are going to simplify to just be 6t squared plus 6 divided by, and we're going to wind up with an 8t cubed. And depending on what you're doing, we could stop there. That is perfectly fine for a free response answer, but we may need to simplify it for maybe a multiple choice answer. I can simplify that with a common factor of 2 in the top and the bottom. Factor out a 2 in the top and the bottom, that would give me 3t squared plus 3 over 4t cubed. So here is the second derivative of the parametric function that we started off with. And the last part of this first example, it says the curve C, which was the parametric function that we started with, has two tangent lines at the point 3, 0, where the curve crosses itself. Find the equations. So this is no different than a lot of other things that we've done in calculus. We're trying to find the equation of a tangent line at a point of at a point of tangency, where the derivative is going to be your instantaneous rate of change. And I feel like I'm not doing that justice, but let's see. We know that we're looking for, what do we have here? We know that at x is equal to 3, we can use the parametric function that we had, which was originally x is equal to t squared. And I can substitute the 3 for the x and say that 3 is equal to t squared. So I can solve this for t and say that here I'm going to get the square root of 3 to be equal to t. Now, considering we may be thinking about this in terms of time, we're probably going to just keep the positive value as opposed to the positive negative square root of 3. And in this case, here, what we're looking for and I'm just taking that point here from the x value that was given to me, and I'll do the same thing with the y value. So at y is equal to 0, basically I'm going to take the second parametric equation that said y was equal to t cubed minus 3t, and I'm going to just substitute the 0 for the y. So I get 0 is equal to t cubed minus 3t, which we can factor that and solve it for t, factor out a t, and then I'm going to get t squared minus 3. So this will give me solutions of t is equal to 0, and again, this one is going to give me t is equal to like a positive or negative square root of 3. Again, probably we'll just stick with the positive solutions, but in this case, because we know we have to have two solutions for the factor in parentheses, I'm going to go ahead and write the positive and negative. Okay. So what this means here, the positive and negative square root of 3 are the only values of t that would result in a point of 3 and 0. So that means we have to evaluate our expression using a square root of 3 in order to figure out what the slope of the tangent line will be, and therefore figuring out what the equation of the line will be. So let's look at the first way that we could do this. Here, if I say dy dx, the derivative of y with respect to x, this is our first derivative that we were looking at earlier. If I'm doing this at t is equal to the square root of 3, we'll look at the positive square root here first. I'm going to, taking the first derivative that I had, which was 3t squared minus 3 over 2t. This is what we got for our result from part B. Go back and find it if you need it, if you don't have it written down. We're going to just do our substitution with the square root of 3 anywhere I have a t. So 3t squared becomes 3 times square root of 3 squared minus 3 in the top over 2t in the bottom, so that becomes 2 times the square root of 3 in the bottom. And that would simplify to be square root of 3 squared is 3. 3 times 3 is 9. 9 minus 3 is going to give me a 6 over a 2 radical 3, which would simplify to be here the 2 and the 6 simplify to be 3 over radical 3, and when I rationalize that, 3 over radical 3 will just simplify to be a square root of 3. So there is one equation of a tangent line, or I'm sorry, one slope. So using the point that they gave me, this point here for x and y, I can say I have one tangent line. So my tangent line in this case will be y is equal to the square root of 3 times x minus 3, and that's as far plus 0 if you want to, but that's it. And now we're going to find the other equation that we could have something where we'd have a positive or negative 3, and I guess we can go back and put a positive negative 3 on there because we are using both values here. So here again, we're looking for the derivative dy dx. This should be dy dx at t is equal to negative square root of 3. And when I do that, I'm going to get 3 times negative radical 3 squared minus 3 over 2 times negative radical 3. And negative radical 3 squared is still a positive 3. 3 times 3 is 3, or 9. 9 minus 3 still gives me a 6 in the top. And I wind up with negative 2 radical 3 in the bottom. So this is going to simplify to be negative radical 3. So my tangent line here will be y is equal to negative square root of 3 times x minus 3. Okay. Now, one of the things that I was looking at this when I was, and so here, let's illustrate what our answers are. One of the problems that I had when I originally looked at this problem is this part here where it says where the curve crosses itself. So what I'd like to do real quick is let's look at this on our calculator and see what it's going to do. So if I go to my calculator here, oops, and I don't remember what that was. Let's just clear it off and go to something else here. So the parametric equation that we have, we're going to go to menu and graph, and we're looking for a parametric function. Now if I graph the parametric function as it was given to me, where I say t squared for the first equation of x, and then for the second equation, what did we have? We had t to the third power minus 3t. if we graph that, this is what I was getting. And I was like, well, where does it cross itself at? How do you know it crosses itself somewhere? And after I played around with it a little bit, I kept wanting, I was determined. I was like, where does it cross itself? And had to play around with it for a little bit. But eventually it occurred to me that the step values that we were looking at here, or the interval of t that we were looking at, wasn't good enough. So if I change that from negative 2 pi to positive 2 pi, I was able to see that yes, it would cross itself here at that point 3,0 that they were telling me that it crossed itself at. And then if we need to verify did we do our material correctly, did we get everything that we were supposed to, we could go ahead and graph the two functions that we had. So let's just graph the functions. So let's look at the tangent lines that we had. The first one that we got was a positive square root of 3 and in parentheses x minus 3. And we wind up with that tangent line there. And it really does look like it's tangent at that point. And the second one that we had was a negative square root of 3 times x minus 3. And yeah, there's our second derivative, or our second tangent line at that point of 3,0 for the parametric function where it crosses itself at 3,0. So that one, I always like to see, well, what does it actually look like? Where do I get it? And I had to see that in this case we had to have t give us some negative numbers in order to actually see where it crossed itself at. And without having t giving us some negative numbers, we wouldn't have been able to see that. So just in case anybody needed to get that for themselves, like I did, there we go. So now now that we've seen, we can find the first derivative and the second derivative of a parametric function, and now how we can write the equation of tangent lines of a parametric function. Now we're going to kind of use that a little bit more, but now we're going to start seeing things that are going to incorporate some trig material. So we're going to need to remember some of that from previous lessons. Here, what it's telling us, the parametric form of a derivative, if a smooth curve C is given by the equations where x is equal to something and y is equal to something, then the slope of the parametric function at the point xy is going to be the derivative of the expression where the dx dt part cannot be equal to 0. That's what we were just doing. And here we're kind of seeing what we would do for second or third derivatives. If you, for some reason, need to do those, there are the templates to kind of help you out with it. We did a second derivative example already. And, whew, so I had something in my throat there. Given the parametric equations, x is equal to 2 cosine theta and y is equal to 3 sine theta, it's asking us to write the rectangular form by eliminating the parameter. Now this is something that was covered in the lesson previous to this one. So if you feel that you remember that material well enough, I would encourage you to go ahead and pause the video and try working it out and see what you get. But let's go ahead and take a look at this first one here. The variable that we're trying to eliminate, where it says by eliminating the parameter in this case, the parameter is theta. We want to get rid of that. So that way we just have something in terms of x and y. Now because they're giving us something in terms of sine and cosine, and we have to be able to eliminate theta in some way, that is going to make me think of using a trig identity. Because based off of what we have for our trig identities, we can, why is that thing there? With the trig identity, like for instance, the basic trig identity, sine squared plus cosine squared equals 1, if I can identify a way of producing that with the two equations that we have, we can successfully eliminate the parameter theta. And that's exactly the approach that I'm going to take here. I'm going to take the x equation, and I want to isolate the trig expression, which would give me, so if I have x is equal to 2 cosine theta, then that would give me x over 2 to be equal to cosine theta. And what I want to do is I'm going to take that equation and I'm going to square both sides. And when I square both sides, I'm going to get x squared over 4 is equal to cosine squared of x. And now let's take a look at this one, and we're basically going to do the same thing here. I have y is equal to 3 sine theta. Get the theta part by itself, the sine by itself, because that has theta. That's what we're trying to eliminate. So divide by 3, and I'm going to get y over 3 is equal to sine theta. And again, I want to square both sides of the equation. So I'll get y squared over 9 to be equal to sine squared of theta. And what I want to do now is to take those two equations and add them together. Okay, so I'm going to take x squared over 4 to be equal to cosine squared of theta, and I'm going to add y squared over 9 equals sine squared of theta. So on the right side of the equation, what we have here is sine squared of theta plus cosine squared of theta. That's your basic trig identity, where that's going to equal 1. So by isolating the terms with theta, sine and cosine, and squaring them and then adding them together, we're creating a way of eliminating the third variable, the parameter of theta, and I'm left with x squared over 4 plus y squared over 9 to be equal to 1. And that is the equation of an ellipse. And I always, don't yell at me if I don't spell this right. I always wonder, is ellipse 1L or 2? But that's the graph, that's the equation of an ellipse. Where the horizontal motion is, of course, going to be the square root of 4. So we have 2 horizontally. We're centered at 0, or centered at the origin. We're going to go 3 vertically in either direction from there. And so we wind up with an ellipse kind of like that. Eye of Sauron. Go ahead and draw it in orange and red and stuff, and there you go. All right, so that is an ellipse, and that's what it's asking us to do. Graph it. What shape did you get? That's an ellipse. So now find the curve of the slope, or dyslexia. I love it. I'm not dyslexic, but I clearly read that backwards, like if I was dyslexic. Find the slope of the curve at theta is equal to pi over 3. Okay. So the slope of the curve is essentially asking us to find the derivative of the curve at that point, when in this case, instead of saying x is equal to something, we're saying theta is equal to something. So this is where we want the derivative of our respective, this is where we need to get that first derivative stuff that we were just practicing. So in this case, we're going to say the derivative of y with respect to theta, dy d theta, okay, from our original function is, in this case, the derivative of a 3 sine theta is going to give me 3 cosine theta. And I need to do the same thing with x, the derivative of x with respect to theta. The derivative of 2 cosine theta will be negative 2 sine theta. And so what I'm going to do now is I'm going to be able to say what the derivative is, dy dx, which would just be 3 cosine theta over negative 2 sine theta. And now that we have our derivative, we can find the slope of the curve at the point that's given to us. Okay, so let's go ahead and do that. So let's find the derivative. Let's find dy dx at x equals, I'm sorry, at theta equals pi over 3 in this case. And so that'll give us 3 cosine pi over 3 over negative 2 sine pi over 3. And simplify and see what we get here. Cosine of pi over 3 is 1/2, so that'll be 3 times 1/2. And sine of pi over 3, that is at radical 3 over 2. And so now we want to simplify that. So I get 3 over 2 over negative radical 3. And that will overall simplify if I multiply by the ratio, by the reciprocal of that, and then rationalize it, we're going to end up with negative radical 3 over 2. So there's the slope of the line at that point of pi over 3. And so the last thing it's asking us to do, it says write the equation of the tangent line. Now in this case, that goes through this point x and y. They're not giving us the point like they gave us on the last one. On the last example, they said use the point 3, 0. We have to be able to figure out what point are we going to be tangent to with that slope. So in this case, I'm going to find my x-coordinate from my parametric equation by just substituting the theta that we had into it. So remember the original x value, the x equation of the parametric function was just x is equal to 2 cosine of theta. So here, substitute theta into there, and I'm going to get 2 cosine pi over 3. And that will give me 2 times 1/2, which would be an x value of 1. My y-coordinate, same thing. I'm going to say take the original parametric equation that we had, which was 3 times sine of theta, do my substitution. So I'm going to get 3 times sine of pi over 3. And that worked out to be radical 3 over 2. So we have 3 times radical 3 over, radical 3 over 2, which will just be 3 radical 3 over 2. So now we have our point 1 and 3 radical 3 over 2. That is the point that we should be tangent to. We have our slope of our tangent line. We have our point that we're going to be tangent to. So the tangent line in this case should be y is equal to negative radical 3 over 2 times x minus 1 plus 3 radical 3 over 2. And there's our tangent line. And I think that may have been what I actually had on the graph a moment ago when we were looking at that. Let's go ahead and graph this here and see what it looks like. Let's try graphing the eclipse. ellipse. Oh, calculator here. And so let's clear the board again. So let's graph equation templates, an ellipse. There we go. And we were centered at the origins. So here this is 0 and 0. And in the bottom we had a 4, so that would be 2 squared and a 3 squared respectively. So if we graph that, there's our ellipse. And the tangent line that we just came up with, let's graph that one. So this will just be a normal function. So we wound up with a negative square root of 3 over 2 for the slope times x minus 1 and plus 3 radical 3 over 2. And there we go. That sure looks tangent to me at when x is 1 and y is equal to, what was it, radical 3 over 2, or 3 radical 3 over 2. So, all right. It looks like we're doing everything okay so far. Now, the next example here that we're going to take a look at, the next two examples are going back to things that we did early in AB calculus, where it's going to ask us to essentially kind of do something with our first or second derivative tests. In this example, find all points, if any, of horizontal and vertical tangency to the curves. So here where they're talking about tangency to the curve, okay, that's where it's indicating that we need to find the derivative. So we're finding derivatives here. Okay, so they're giving us a parametric parametric function, the two equations, one in terms of x, one in terms of y. So we're going to find the two derivatives. So we'll say dy dx, nope, dy dt in this case, dt. The derivative of that will be 2t squared minus 3. Nope, that would be 3, not 2, wouldn't it? 3t squared, there we go, 3t squared minus 3. And the derivative of this one, of x, dx dt, would just be a 1. So what we're going to be working with here, let's go back to green, I guess. When we say we want the derivative, dy dx, that would just be 3t squared minus 3 over 1, which is just 3t squared minus 3. Okay. All right, so, and use a graphing utility to confirm your results. Okay, so we'll do that. I've already done it a couple times already. So this is what I want to ask myself here. Since I'm talking about doing something with derivatives, okay, this is what I need to know. At what value of t will the derivative equal 0? That's usually what we think of whenever anything we're talking about finding the slope of the tangent lines. We're we want to know when will the derivative equal to 0 based off of that derivative that we have. So in this case, I'm going to take the 3t squared minus 3, and I'm going to set it equal to 0, and I'm going to solve for t. So move the 3 over, so 3t squared is equal to 3, so that means t squared is equal to 1, so t should be a positive negative 1. Okay, so we know we have a positive negative 1 now, so let's take a look at we have the two parametric equations. When time is equal to 1 and when negative 1, we need to know what coordinates would we have. So at time equals positive 1, we're going to say that x would be equal to 1 plus 4. So I have an x value of 5. I'm going to say y is equal to 1 cubed minus 3 times 1. So 1 minus 3 says that the y value here will be negative 2. So I have a point here at 5, negative 2. Okay? And let's see. That should be a horizontal tangent line, if I'm not mistaken. That should be a horizontal tangent line. And let's look at it for the other example here. What color haven't I used? Let's do black here. So at t is equal to negative 1, when I do my substitution here, I'm going to say for x, I'm going to get negative 1 plus 4. So I get an x value of 3, and y equals negative 1 cubed minus 3 times negative 1, and that will give me y to be equal to a positive 2. So I have here 3 and positive 2, and that will also be a horizontal tangent line. And we don't have any vertical tangent lines on this one. And it's not asking us to write any equations or anything like that, but let's go ahead and see if we can actually graph the parametric function and see what we get. Nope, calculator. Let's go to calculator. So let's clear this off and let's graph a parametric. So we had t plus 4 for the x equation. We have t to the third power minus 3t for the y equation. We have that function. And let's see. So here I see the point 5, negative 2, which was when we had t was equal to 1. But what about the negative 1? Well, I'm not seeing anything. Let's change our step here, or let's change our, let's change our t value here, see if that will help. So again, let's change it back to negative 2 pi, just to give us room. Okay, so there we go. And there's the other horizontal tangent line at 3, 0. And you can see, looking at the graph, it doesn't look like we're going to have any vertical tangent lines. So here, by doing that, we're able to identify the negative 3 and positive 2 and the positive 5 and negative 2. That correlates to what we were doing for the first derivative test. Essentially, we're kind of identifying where we have local extrema, in this case of the parametric function. So, all right, cool. So let's go back to the notes here and see what we have next on tap. Determine the intervals on which the curve is concave up or concave down. Well, there's your key word. in letting you know what you're doing. Concave up or concave down, that's your second derivative test. So we need to find the second derivative of the parametric function that we currently have. So let's start it off with what we've been doing. Let's find the first derivative, obviously. So we're going to say dy dt. In this case, the derivative of cosine of t will be negative sine of t dx dt. The derivative of sine of t is just going to be cosine of t. So here if I say dy dt, or dy dx I should say, that'll give me negative sine of t over cosine of t, which we could, if we wanted to, we could just say that that would be the negative tangent of t. So we have our first derivative. So now we're going to say our second derivative. So we'll do that in a different color here. So my second derivative, I'll do that in green. The second derivative, d squared y over dx squared, in this case is going to be, remembering what we had before, we had d dt of dy dx over dx dt. So let's substitute what we have. So the d dt, again, that's just indicating that we're taking the derivative of what's in the parentheses. So in this case, in the parentheses, I'm going to put negative sine of t over cosine of t, because I think that'll probably be easier to do than tangent for the derivative. And dx dt is just going to be cosine of t. So inside of the parentheses, for negative sine of t over cosine of t, I'm going to do the quotient rule again. Low d high minus high d low over low low is going to give me negative, I didn't do that, let's start that over here. This one is going to wind up giving me a negative cosine of t times cosine of t minus a sine of t times a sine of t over low low, which would just be cosine squared of t, cosine squared of t. And all of that is over cosine of tangent, or cosine of t, I should say. So instead of saying divided by cosine of t, I'm going to multiply by its reciprocal, 1 over cosine of t. And what we see in the numerator is almost the trig identity. Instead of saying cosine squared plus sine squared, we have negative cosine squared minus sine squared. So instead of getting a positive 1 in the numerator, I'm going to wind up getting a negative 1 in the numerator. And in the denominator, cosine squared times cosine will give me cosine cubed of t. So here is the second derivative. Now what we're using, now we need that second derivative in order to determine where is, on what intervals is it going to be concave up or concave down. So we have to do a candidates test here. So our candidates test, we need to be able to identify the upper and lower bounds of the interval. So we know that the lower bound is 0. So here at 0, and the upper bound is going to be at pi. But there's got to be some other place between 0 and pi where I'm going to have something that will be 0. So let me take a look at this. Let's see, so we have cosine cubed. So I want to know where is cosine cubed of t going to be equal to 0? And in this case, that should be, according to what we know on the unit circle, that's just going to be at time is equal to pi over 2. At 90 degrees, cosine is 0. So there we have pi over 2. So if I pick something to the left of pi over 2, let's say our candidates test, let's say pi over 4. Well, pi over 4, if I substitute that into pi over 4 of cosine is going to be radical 2 over 2. That's just cosine of radical, or cosine of pi over 4. Now if I cube it, I get a positive number, and I have a negative number overall in the second derivative, so that's going to give me a negative value here. And if I pick a number that's greater than pi over 2 but less than pi, let's say 3 pi over 4, well, 3 pi over 4 is actually going to be a negative number. That is going to be negative radical 2 over 2. So if I cube that number in the denominator, if I cube that number, I get a negative number, but I have a negative in the numerator, so that would create a positive value. Okay? So in this case, the intervals where it's going to be concave up or concave down, here it's concave down, and here it's concave up, because that's what the signs indicate. So in the interval here that I would answer is I would say we are concave down on the interval from 0 to pi over 2. And we are concave up on the interval from pi over 2 to pi. And that is how we've been using. So again, not a new skill necessarily, or not a new concept of doing the second derivatives test to check for concavity. The new thing is just finding the first and second derivatives of a parametric equation. So here, this is where we're going to start talking about how we can use the parametric equations to find ultimately we're going to be looking for the length of an arc of a given parametric function. We know parametric equations describe a path of an object moving on a plane somewhere, and so that leads us to thinking, well, how far did it go? And it's giving us the equation here. The absolute value of the velocity is going to be the square root of dx dt squared plus dy dt squared. It should look very familiar, that type of formula. That's how we are going to determine the velocity. We can find the distance that that object can move by taking the integral of that velocity function. So we can think of this as kind of the average rate of change, and this, we can think of this as the instantaneous rate of change. So when we look at those two things together, the length of the arc in parametric form is the integration of function v, of the velocity function with respect to time, on whatever your interval is from a to b. And so we ultimately end up with the dt is going to be equal, the distance traveled is going to be equal to the definite integral from a to b of the square root of the derivative of f squared plus the derivative of g squared with respect to t. And that is where we come to our next example. Okay. Well, looks like it's time to go home or something here. bell just rang. Find the length of one arch of the cycloid with a parametric equation of x is equal to theta minus sine of theta and y is equal to 1 minus cosine theta. Well, there's one thing that I want to make sure that we all understand here. What is one arch? What does that actually mean? Okay. Here, one arch is usually going to be considered from 0 to 2 pi. That's what one arch is. Okay. Now, in this case, it's asking us to do this with a calculator. Those of you that have the notes that come along with this, on this example, there over here somewhere, there's that calculator diagram. And this one is very easy to do if you're going to use a calculator. But I think I'll probably do the work for it just to make sure that everybody can get it okay. So here we're going to kind of do the same things that we were doing. We're talking about finding the length of something. So the length or the distance that we've traveled is going to be the integration, in this case, from 0 to 2 pi of the derivative of x is the square root of dx dt. Oop, I didn't mean to put that close parentheses there. Squared plus dy dt squared with respect to time. That's essentially what we're looking at. That's the formula that they gave us. So let's figure out what the derivatives of those are. And here we're going to go from 0 to 2 pi square root. So the derivative of x, the derivative of this is just going to be 1 minus cosine of theta. So here I'm going to get 1 minus cosine of theta quantity squared. The derivative of y with respect to time, that's just going to be cosine is negative sine, so negative negative makes this a positive sine of theta quantity squared dt. Actually, no, that should be, in this case, this is going to be theta, d theta. Here, because this is a calculator exercise, you could type that into your calculator, and it's going to give you 8 for your length. Okay. Now, is this one possible to do without a calculator? Yes, of course it is. So I'm going to go ahead and finish working this one out as if it wasn't asking us to do this on a calculator. And if you want to write this down and include it in your notes, then great, go for it. If not, you can kind of fast forward and move to the last example. So we have 0 to 2 pi again. And when I expand the 1 minus cosine of theta squared, that's going to give me 1 plus 2 cosine of theta plus cosine squared of theta. And if I square sine of theta, that's just going to be sine squared of theta d theta. And of course here, this is your trig identity. So that's going to be a 1. So 1 and 1 are going to give me 2. So that'll be 0 to 2 pi. And so that'll give me the square root of 2. And I have something wrong here. Oh yeah, this will be negative and negative. This should be negative 1 minus 2 cosine. There we go. So this will be 2 minus 2 cosine of theta d theta. And again, you could type that part into your calculator there again and show that that one's going to be equal to 8. But let's go ahead and kind of finish taking a look at this here. The way that I would continue working this particular problem, because we have something trig related, we're still going to be thinking, is there a way that I have like some identity or like a half angle, double angle, anything that's trig related that I could use to kind of, you know, clean this up a little bit? Well, we can separate the function here. The inside of the radicand right now, we have a common factor of 2 that I can factor out, which would be the square root of 2 times the square root of 1 minus cosine of theta d theta. And one of our trig identities that we have been uh, presented with in the past is something that looks like this. If I have sine squared of theta, that is going to be equal to 1 minus cosine of theta over 2. And this is kind of where we're seeing the similarity with a trig identity that we've seen before. So if we take that 2 and we wind up multiplying it to the other side, we're going to actually wind up with 2 sine squared of theta over 2 to be equal to 1 minus cosine of theta. So I can take that and substitute it underneath the radicals. So I'm going to take, let's go back to my blue here. I'm actually going to take this radical out as not to the other side of the equal sign, but I'm going to take this radical out as a constant, and I'll take this and substitute it here for the 1 minus cosine of theta, and that'll give me square root of 2 times the integral 0 to 2 pi of square root of 2 times sine squared of theta over 2 d theta. And again, I'm going to kind of separate the square root that we have to be the square root of 2 times the square root of sine squared theta over 2 d theta. And that will also come out as a constant. So radical 2 times radical 2 will just be 2, 0 to 2 pi. I'm running out of space here. Give myself some more. And we have the square root of sine squared of theta over 2 d theta. And the nice thing about what we've done by identifying the trig parts that we can work with, we have the square root of sine squared now. And the square root of sine squared is just going to be sine. So here I have 2 times the integral 0 to 2 pi of sine of theta over 2 d theta. And here, this is where I want to start thinking about doing u substitution when I start to do my antiderivative here. So let's, again, go to a different color here. So I'm going to look at u to be theta over 2. So du in this case will be 1/2 d theta. And we don't have the 1/2 in the integral so far, so multiply both sides by 2, and I'll get a new constant of 2 to be d theta. So we're going to get, let's see, we're going to get the 2 times the 2 that's already there, times 2, so that'll give us our 4. And I want to know what my integral is going to be using u substitution here. So now In this case, when theta is equal to 0, what's u going to be? Uh, so in this case, 0 divided by 2 says that u is just going to be 0. And when theta is equal to 2 pi, if I say 2 pi over 2, that means u in this case is just going to be pi. So my upper and lower bounds didn't change. So let's go here. We have 0 to pi of sine of u du. And now we can actually take the antiderivative. So the 2 and 2 are going to give me a 4 here. The antiderivative of cosine is going to be negative, I'm sorry, the antiderivative of sine is going to be negative cosine of u. And we're evaluating it from 0 to pi, so we're really just evaluating it at pi. Actually, no, in this case, we have to use the lower bound of 0, because I always forget. I usually like having 0 as my lower bound, because I think it means I don't have to do substitution with 0. But with the trig stuff, we do. So we have 4 times negative cosine of pi minus negative cosine of 0. And cosine of pi is going to be negative 1. I'm sorry, cosine of pi, yeah, what do we have here? So all of the stuff that's in the parentheses here, or in the brackets, the negative cosine of pi, yeah, or cosine of pi on our unit circle will be negative 1. Cosine of 0 is going to be positive 1, but then I have the double negative, so that becomes positive 1. And that becomes positive 1 plus 1, and you can see that's going to be 2. 4 times 2 is where we get an 8. So I understand that was a bit of a lengthy aside for something that was telling you that it was a calculator problem. And I could see why you would probably want to do this on a calculator, because this is not necessarily an easy integration problem. Once we get to a certain point, it's not very, painful, but identifying some of the things that we can do with the trig stuff to get to the point where it's not going to be painful, it is not exactly the coolest problem in the world to do by hand. I get it. Either way, we get 8. Okay, so here's the last one. So if you fast forwarded through the last example, you're ready here. Let's see. The path of a baseball is modeled by parametric equations given below, where x and y are measured in feet, and find the difference between the horizontal distance and the length of the path of the ball. So the length of the length that the ball actually travels is going to be on an arc when you hit it, presuming that it's like a pop fly or something that's going to go to the outfield, rather than like say maybe a line drive or a grounder. But let's see what we have here. Now, I can tell looking at the example that it's not telling us what t is measured in here. Those of you that are following along with the notes for this stuff, it does say that x and y are measured in feet, but right here it also says that and t is supposed to be measured in seconds. Not sure if that's necessarily necessary for this problem, but okay, let's see what we get. Now again, this one is telling you, it has on the diagram, for those of you following along with your notes, it tells you that we're using a calculator. And this one you really do need a calculator for, and it's not going to be the kind of problem that you can just plug something in at the beginning of the problem and be done with. This is the kind of problem that would be I wouldn't necessarily say that a baseball problem is going to be something that you might see as a free response question on your AP exam, but the skills that we're going to see here very much I could see as being like a free response calculator question where you need to make sure that you save your numbers and don't introduce any kind of rounding error. So whatever calculator that you're using for this, we are going to be saving some numbers on it, so make sure you know how to do that before you begin the problem for whatever device it is that you have. Now, the one thing that I want to make sure that we point out very clearly, because this one wasn't obvious to me when I first started working this problem out. Notice the symbol that we have here. Here, we're not in radians here. We're going to be working in degree mode. So make sure your calculator is in degree mode when we work this particular problem out. And so let's see what we're going to be working with here. If I type x is equal to, or if I type the 70 cosine of 50 on my calculator here, let's see, what am I looking at here? Trying to make sense of my notes. Hold on, I'm going to pause this for a second because I'm forgetting something real quick. Okay, I see what it was. The way that this problem is presented here on the slide is not the same as it was on the paper that I'm looking at that I did my notes with before, but it's okay. For instance, on the paper, it says x is equal to 70, and it has parentheses like this, 70 cosine 50 degrees t like that. And that's what was throwing me off. Something kind of looked off. But anyway, basically what we're going to do is we're going to go to our calculator and we're going to say, well, what is x going to be equal to? What is 70 cosine of 50 degrees? So here, x is going to be equal to about 44.995 t. Now you need to save that number in your calculator. I saved it in memory spot A, okay, because clearly I'm rounding that number, and we're going to use that number again. And I want to know what is 70 sine of 50 for my y value. So for my y equation, I'm going to wind up with 2.5 plus, and 70 sine of 50 on the calculator gave me about 53.623 t minus 16t squared. And you need to save that number in your calculator. I saved that number in my memory spot B, just in case if you're following along with the same. I always start, in the first memory spot and then just go through. So A through B or A through Z, whatever we wind up with. Okay. Now, what we need here is we need a value of time. Okay. We do need a value of time. It is definitely going to be the fact that seconds was missing. I do think is kind of important here because what is the time value? So this right here, let me pick another color. This equation right here, because it's in the form of a quadratic, I can use this to solve for time. So that's exactly what I'm going to do. I'm going to use the quadratic formula to solve for time here. So in this case, time is going to be equal to negative 53.623 plus minus the square root of 53.623 squared minus 4 times a, which in this case is negative 16, times c, which would be 2.5, divided by 2a, so that would be 2 times negative 16, or you could just write that as negative 32. And I'm going to my calculator to do this, okay? So when I do this on my calculator, I'm getting a time value of negative 0.046 and 3.397 seconds. So because we are talking about this in terms of time, we can throw the negative value away because we're not going to be working with anything that has a negative value for time. So I'm going to take that 3.397 seconds and I'm going to save that number. So that's 3 numbers that I've saved on my calculator so far. All right. Well, why do I need that time value? That time value is going to be important because here this can be used to find x, which would represent your horizontal distance traveled. So let's find x. So I'm going to just take that number and just plug it right into the example that we have here. So we have x is equal to what did we have? The 44.995, that number that we saved, A, times the 3.397 number that I said times C. And when you type, or you can, say 70 cosine 50, and then type it, hit that 3.397 number. Either way, you should get x to be about 152.868 feet. So there's the horizontal distance. Well, now we need the length of the arc to compare them to. So the length of the arc is similar to what we did on the last example here, where I'm going to say the length of the arc is going to be the integration from something to something, for, in this case, time. So it's going to be from 0 to the 3 point, what did I have? 397 seconds of the square root of the derivative of x and the derivative of y. So the derivative of x is just going to be the number 44.995 squared plus, and the derivative of y is going to be the 53.626 plus, nope, not plus, minus 32t quantity squared. And here we're doing everything with respect to time. So if you have those numbers saved on your calculator, this is an easy thing to type in with your integration. And here, the approximate value of this is going to be 184.489 feet. So how do they compare? Well, we're going to just take the difference of this number here and this number here and say the difference, just subtract them from each other, the difference in the arc versus the horizontal length is going to be about 31.621. So the way that I would say this is I would say the ball traveled 31.621 feet further along the arc than it did horizontally. Now, let me look at the question one more time here because, let's see, one of the things that it's asking us to do on the handout for the notes is does it say to graph it? Graph the path. Here it doesn't say graph the path. On the notes of the handout that you have, it does say graph the path. So let's go ahead and do that. I know it doesn't look like it says it here. Just find the difference between them. So if we graphed it, I'll just use this blank space here. If we graphed it based off of the position function, and let me do this one here in a different color. Based off of the position function that we have, it starts at 2.5 feet above the ground. The player is going to hit it, and it's going to travel in some kind of a parabolic arc like this. And the x-axis is going to represent time. So where it hits here, that is the time that we got of 3.397 seconds. And I think that's really all we needed to do for the graph. Yeah, so because the distance that we traveled isn't going to show up on this particular function, we could write the horizontal or the arc length, I guess, there, but that's all we have here. So again, this is just to kind of recap what we were talking about. We're finding the derivatives of parametric functions, finding the slopes of tangent lines of parametric functions. We're talking about how we can use, say, first or second derivatives of parametric functions to do what we did in AB calculus and find local extrema, intervals of concavity. And the last couple of problems that we see here, we're practicing, actually using the parametric functions themselves to find the length of something using the derivatives of the parametric functions of the individual pieces. So that's going to wrap it up for this particular lesson. Thank you very much for watching. I hope you got some beneficial information out of it. But until next time, ladies and gentlemen, thanks for watching and take care.